So a Poisson distribution. So it is what we call a counting distribution or a distribution of counts. For example, the number of sandwiches sold per hour at a deli, right? That would have a Poisson distribution. Another example, number of people who join a gym per month, right? With different gyms, we can discuss it. And all of those are counts, yes.
Would this have you like rates?
But this is a rate though. That's a good question. She read number. So we're talking about per hour, per month, per something. So these are all rates. Now, does it have to be a rate? Not necessarily. It could just be a count. We could simply say the number of people who join a gym. Right? That's perfectly fine. But in practice, when we talk about Poisson distribution, we sort of put a unit of time, unit of space. It could even be, you know, the number of ants per square centimeter of the yard, right? If you have the time to sit and count the ants. So, typical example. So, the way I like to define a Poisson is lambda t. Now, why do I do it this way? This is more formal. And let's say x is the count. So the number of whatever, number of sandwiches sold per hour, number of people who join a gym per month. What is the support of x? 0, 1, 2, just n. Infinity, you can keep on going, right? It doesn't have to tell you. So if that is the case, then that is the formula. So that is the PMF of a Poisson. If t is equal to 1, then this would reduce to lambda raised k, e raised minus lambda, divided by a factorial, k equals 0, 1, 2, dot, dot. Right? So in case 2, lambda is a rate. In case 1, lambda t is a rate. What do I mean by that? Let's say the number of sandwiches sold per hour at a deli is 10. And if someone came and asked you, well, if I'll write it so that you don't get confused. Let's say the number of sandwiches sold per hour at a deli. And I'm going to say X is Poisson, just lambda 10. So in this case, lambda equals 10 means 10 per hour. Good. Now if I asked you, well, what is the distribution of y, which is number of sandwiches sold per 30 minutes? At a deli. What would your answer be? So, fine. Now, Poisson has this property that you divide it at the right intervals. So y would be Poisson 5. Correct. So this would be lambda x. This would be lambda y. New rate, it would be 5 per half an hour, right? So instead of computing a new lambda each and every time in doing any sort of problem, why not stick with this? If t is any unit of measurement, if it is per hour, what should t be? Well, what value is that? 1. If I said half an hour, what should t be? 2. A half. 15 minutes. A fourth. 10 minutes. A sixth. Right. So all I have to do is change the t value and use the same formula, which is why this is more effective than that. Instead of changing the lambda and calculating each and every time. Are they equivalent? Most certainly, they are one the same. But intuitively, this is better and effective. Don't you agree? I think so. But if you want to do it this way, go ahead. A PMF. Huh?
You say you do it that or not that way?
X, the first way is better. Yeah. In my opinion. Then opinions differ. We want to know if it is a valid PMF. How do we verify?
Nothing's bigger than 1. Sum 1.
They have to sum to 1. Clearly, it's not going to be bigger than 1. If I can show that everything sums to 1, then the numbers that I have better be less than or equal to 1 and greater than or equal to 0, because I know it can't be negative. So I'm going to sum them. k equals 0 to infinity. Lambda t raised k e raised minus lambda t over k factorial. So I'm summing the PMF for all possible values in the sample space for x. And do we see any consonants here? Exponential part doesn't have a k in it. So e raised negative lambda t, sum k equals 0 to infinity, lambda t raised k over k factorial. Yes, and what is that? E raised lambda t, that is Taylor's series of e raised lambda t. So we have e raised negative lambda t multiplied by e raised positive lambda t. This one. So it is a valid PMF, it better be. So it has to be on its entire support. We're multiplying k and e raised negative lambda t raised k divided by k minus 1 factorial. Yes. So my mind is going ahead. K equals 0 to infinity. I can write the denominator as k times k minus 1 factorial. The k's will go away. And e raised negative lambda t is a constant. I surely can't start at 0 because I'll end up getting negative 1. So start at 1 up to infinity. So lambda t raised k divided by k minus 1 factorial. That isn't doing any good yet. But when I do the trick of adding 1 and subtracting 1, I will have e raised minus lambda t sum k equals 1 to infinity, lambda t raised k minus 1 times lambda t. Correct. So lambda t can come out now. So e raised minus lambda t times lambda t times sum k equals 1 to infinity, lambda t raised k minus 1 over k minus 1 factorial. If you expand this sum out, you will get 1 plus lambda t over 1 factorial, lambda squared, lambda t whole squared divided by 2 factorial, plus dot dot dot. Yes, you plug in each value, that's what you get. But we know that's the Taylor series expansion for e raised lambda t. So that would become so if you multiply this term and that term, when you multiply, it's going to become 1. So you will get lambda t. Good. Now, variance, it is a bit tricky. I'll do the variance part. So we know that the variance of x squared is simply the expectation of x squared minus the expectation of x whole squared. I'm going to do a trick, and you will know as to why I'm doing this when I get into finding the expectation. So add x, subtract x. There is another way of doing this, but I'm going to take this approach. I can move that expectation of negative x outside. Oh. Keep the negative inside, take the positive outside. Good. So that would be expectation of x multiplied by x minus 1. Good. Now finding expectation of x times x minus 1 is what we need. Erase this.
Oh, hold on, before you do that, in the middle column that you were about to erase, what's the exponent say?
This one?
Yeah.
Plus 1 minus 1.
And there's no negative in the lambda t numerator.
No.
Oh.
So we want to find the expectation of x times x minus 1. That would equal to some k equals 0 to infinity. If it is x times x minus 1, it is a function of x. There is a property, which is from last time. Lotus, law of the unconscious statistician. So this is a function of x, so I can just throw that in there. So k times k minus 1 multiplied by e raised negative lambda t raised k divided by k factorial. Good. So have k times k minus 1 e raised negative lambda t, denominator k times k minus 1 times k minus 2 factorial. Good. Numerator, have lambda t raised k. And now you can see as to why I started with the expectation of x times x minus 1. Because at this step, it'll get cancelled. So those two would go away. E raised negative lambda t is a constant, so I can pull that out. And we have lambda t raised k divided by k minus 2 factorial. Clearly, where should it start? 2. So what trick should I use? Plus 2 minus 2. So e raised minus lambda t, sum k equals 2 to infinity. Lambda t raised k minus 2 divided by k minus 2 factorial. And outside, well, let me not skip a step. I'll just put lambda t squared. Good. And that's what I would have. And if you plug in 2, 3, 4, all the way up to infinity, what would that reduce to? E raised lambda t. So e raised negative lambda t multiplied by lambda t squared multiplied by e raised positive lambda t. Those two will go away. We'll simply have lambda t squared. Yes?
Is what everything after the summation was.
This entire summation will reduce to e raised lambda t. So going back to this step right here, variance of x is equal to the expectation of x times x minus 1, which we have found to be lambda squared t squared or lambda t squared, plus the expectation of x which is lambda t, minus expectation of x whole squared, which is also lambda t. So lambda t whole squared. Those two will get cancelled. So you will have lambda t. Good. So for a Poisson random variable, the mean and the variance are one and the same. So of choice. So the number of people who enter Griffin Hall per day X is X, and that is Poisson 243. What is the probability? Exactly 400 students enter Griffin Hall on 2 days. What is the probability that at most 100 students enter Griffin Hall on a single day? So what we have is X is Poisson 243. So that is our lambda t. So lambda t is 243. In other words, 243 per day. T is 1. Now we want to find the probability that exactly 400 students enter Griffin Hall on 2 days. So if it is 2 days, then the rate is going to change. For 1 day, it is 243. So 2 days, it will be 486. So that's what we need, right? So all I did was take that lambda that I have and multiply it by T2. Now you may say, well, really doesn't matter whether I have lambda or lambda T. Why do you find this to be easier? Well, certain experiments, chemistry and stuff, you may want to convert from 0.1 nanometers to 0.001 micrometers, right? At that time, using a time unit or a time convention is better because it's not always time. It could be time, it could be length, it could be volume, it could be space, it could be pressure, it could be any unit of measurement, okay? But oftentimes we use time. But T is any unit of measurement because it's a rate. So Y is Poisson 486, and it is for 2 days. And you can use this Poisson PDF on your calculator. 486,400, which is lambda, x. And what is that answer?
6.039 times 10 to the minus 6.
6 in a million chance that that would happen. Does that make sense? Why, Shay?
There's just a lot of different possibilities for like a single individual number of students happening, right?
Okay. Close. Any other answers? So, go ahead.
Like I say, it's probably further than 3 standard deviations. Oh.
That's another way of doing it. I'm going to do it later. So if you look at this, I'm asking for this is a very strict condition, right? exactly 400. I want 400 to happen. And the probability of that is going to be small because if it is an exact probability, I'm specifically looking for one outcome. And that is going to be low. But if I change it and said, what is the probability that we would see at least 400 or at most 400, this probability will go up. Yes? Let's see. What is the probability we have at most 100 students enter Griffin Hall on a single day? So that would mean it is the probability x is less than or equal to 100. And we know x is Poisson 243. Even before you start the problem, do you expect this probability to be very small or very large? It has to be very small. Why? Why? So much lower than the average. What is so much, Joe?
3 standard deviations.
3 standard deviations, 2 standard deviations. Where does it come from? The 3, the 2?
That's a really good question. I don't know.
3 standard deviations, 2 standard deviations.
Like
99.7%. Yeah.
The
The bell curve is empirical. Now, there are some conditions for me to use this in this problem. I think it'll be satisfied. But so 243, yes, that is the expected value of mu. Square root of lambda t will give me the standard deviation. In this case, square root of 243. Approximately 16.
13.5.
I'll round it to 16 because we don't want half a person coming in to Benton.
Yeah.
Like, probably bleed to death. So 243, 2 standard deviations. I could even push it and go 3 standard deviations to the right. That's adding 48 to it. So that is 297 mu plus 3 times sigma. On this side, I'm subtracting.
243 plus 48 is 291.
Oh, sorry, 291. Thank you. On this side, I am subtracting 48 to 43 and 195. Right? The standard deviation is sigma. Right? So by all means, if that is true, I'm saying, or I know, a reasonable interval of students would be from 195 all the way up to 291 inclusive. So that is the most likely thing to happen. Anything else would be, close to impossible. It's a miracle. So that said, where does 100 lie?
Around the 9 standard deviation board.
Way over here somewhere.
Well, exactly 9 is below.
So the most likely possibilities are here. So is it feasible for us to see somewhere between 195 and 200 students? Yeah. Less than 243 students? Yes. That would be exactly 50%. But since 100 is way out of that range, it has to be a small probability. So if you use Poisson's CTF, these French names, 243, 100. And that is
190 times 10 to the negative 5.
still not zero, because zero would be impossible. Still not zero. It could happen someday, billions of years from today, if this building still exists. And if that is true, we might have at most 100 students.
Yeah,
Yeah.
without COVID, it probably was less than 100.
No, but the conditions have changed. Right? There's one other thing that I wanted to mention. What if instead of at most we had at least? We have to do 1 minus and then 1 less, right? So don't forget that. So do we understand, Poisson?